What we're attempting to do is use virtual environment technology to solve a real engineering problem. In our case, it's the interactive visualization of three-dimensional flows. So the whole point is we want it to be like a real wind tunnel, except that you are there and you're not disturbing anything.
To provide the illusion of being surrounded by flow, a unique head-tracking display system is used. A pair of video CRT monitors are used to present high-resolution, wide-field images in binocular stereo to the virtual wind tunnel user. The weight of the monitors is borne by a gimbaled, counterweighted, 6 degree of freedom motion platform known as the boom. Optical encoders at each of the 6 joints of the boom provide high-speed, high-precision information about the position and orientation of the user's head. A high-end graphics workstation renders the virtual wind tunnel imagery in real time, in stereo, from the user's point of view. Manipulation of the flow visualization tools within the virtual wind tunnel is accomplished by using an instrumented glove. The glove senses the position, orientation, and gesture of the user's hand. A variety of gestures are recognized by the system and are used to control the flow visualization process. A small, cross-shaped cursor tracks the user's hand position inside the virtual wind tunnel. A streamline is computed through the flow starting at the hand position. This represents the path that a particle would travel if it were emitted into the flow. A hand gesture freezes a streamline at the current hand position. Another gesture controls a collection of streamlines known as a rake. In addition to tracking the position of the hand, the rake also tracks the hand's orientation. Note the diverging behavior of neighboring streamlines. Some go above the wing and are caught up in the wingtip vortex. Others are caught up in the wing root vortex. And others go completely under the wing. We can scale the data and then walk around inside the vortex, examining its structure in detail. By simply changing databases, the user of the virtual wind tunnel can view other flow simulations. Here we're looking at a simulation of flow around an ogive cylinder at an extreme angle of attack. This is being used to test an experimental method for aircraft control. High-velocity airstreams are injected into the flow. Notice the complex asymmetrical flow patterns. Some of the most challenging computational aerodynamic problems involve three-dimensional flows that change over time. Here we see non-periodic vortex shedding past a slightly tapered cylinder. The flow is visualized by placing a line of virtual smoke emitters along each side of the cylinder. The vortex shedding process can be clearly seen. Smoke circulates for a while near the cylinder and then breaks off and travels downstream. We can freeze time and examine these complex flow structures by walking around them. A wide variety of interactive techniques are being developed to visualize these unsteady flows. The integration of these techniques is the next phase of virtual wind tunnel development. Team member Steve Bryson describes the project's future.
So over the next couple of years, what we're going to see is a very rich environment where the user will get into the virtual environment and have a wide range of options of ways of visualizing the flow that hopefully can change from one option to another very quickly. And the real challenge is to make all of those options very intuitive so that the user doesn't need to do a great deal of learning in order to use the system. He can get in and use it very quickly using all his intuitions. And that way he can concentrate on the science of the problem.
The Virtual Wind Tunnel project will provide scientists with a highly intuitive environment for exploring complex aerodynamic flows.
Here we see the current state of the virtual wind tunnel.
What you had just seen in this tape was a prototype circa 1991. This is circa fall of 1993. It uses much more sophisticated full aircraft data sets, and it's capable of showing other phenomena in unsteady flow. For example, here we show bubbles or particles being injected into a flow beneath a hovering Harrier jump jet simulation by Chawla, Van Dalsum, and Smith. Instead of having streamlines or other tools directly attached to the user's hand, in this case we have the tools sitting out in space and they can be grabbed, much as objects in the real world, as you see an example there of us moving the emitter of the particles that you see. In order to facilitate grabbing, we had those large balls show up when you were ready to grab the rig. To control the visualization tools, we have widgets analogous to sliders. For example, we just changed the number of particle emitters in this particular visualization device. This particular data set has 3 million data points, which are some 50 megabytes apiece, so the data management problem is quite serious. There you see the use of menus in the virtual environment to change the properties of the tools. For example, we just changed this into streamlines. Through a creative use of tools such as menus and sliders and having objects that you can grab and manipulate, we've reduced the number of gestures required to operate this environment to just 2, simply grab and point. What we're doing now is decreasing the number of streamlines so we can get very high performance. The computations involved in this particular application are quite severe. What you're seeing is running on a Silicon Graphics 380 VGX for the interface handling and the graphics, and the computations are taking place in a Convex C3240 computer. It's a distributed application. The hand commands are being sent to the Convex computer over a gigabit network, the Ultranet. The Convex computes those streamlines you see and then ships them back, and the Silicon Graphics machine draws them. So this is a distributed application, and because of the design I just described, it's fairly easy to hook 2 separate virtual reality stations to it, so you can have 2 people viewing the same environment and interacting with the same environment. Some experiments in shaping of surfaces in virtual reality via direct manipulation of the surface. This particular paradigm uses a point-like grab of the surface, where you grab the surface like so and lift it up, and then the area of influence of that move are controlled by various mathematical functions, which are analogous to Alan Barr's spatially weighted transformations. It turns out that trying to map an entire glove or other such anthropomorphic devices to a surface is a very non-trivial problem.